Exercise 2F, linear Diophantine equations. In this exercise, I'm going to introduce these equations to you. We'll discuss a proof, and I have another video of it that will, for those of you who need to step out, they exist. And our exercise or example for this class is an application of it. And your pre-learning is questions 1 to 4 in the textbook, okay? So let's define our equation. AX plus BY equals C. Now, here is the textbook definition of it. So you can see, but A and B are integers, so is C. And X and Y have to be integer solutions for this. Okay, so X and Y are the variables. A, B, and C stay the same through the whole equation. How many different pairs of X and Y can we find? The other thing to mention is there are many other classes of Diophantine equations, but our focus is on the linear ones. Okay, so reading the textbook, they did mention something like x squared plus y squared equals z squared could be considered as a Diophantine equation, and so linear solutions to that are your Pythagorean triples, right? 3 squared plus 4 squared equals 5 squared, yada yada. All right, so the equation we're going to consider is this one at the bottom here, 3x plus 4y equals 1. Now I've highlighted these colors for a reason. Hopefully it makes things clearer for you. So 3, 4, and 1 are integers, and the values of x and y that satisfy these equations both have to be integers. So let's find one. Okay, so let's assume y is equal to 1. Then 3x plus 4y equals 1. So 3x equals 3, minus 3, sorry, because I've subtracted the 4 over. So x has to equal minus 1. And let's go back and check. 3 times minus 1 plus 4 times 1 equals 1. And we could go through and do this many times, but our initial pair here is x is minus 1, y is 1. Okay, and here's a graph of many other solutions. Take it from your textbook. Okay, so this one circled here is our initial one. But if you look at any of these other values here, 3 times 3, x value is 9, and 4 times minus 2 is minus 8. 9 plus minus 8 is 1. And the same would be true for all those values. Okay, so let's call these points x0, y0. x0, y0 is just saying the initial one we've found. Okay, so let's have a look at this table I've drawn here and relate it back to the values here. And all these values are values of our solutions here from this graph. So you can see that from our equation, and let me write that out down here again. I'll just copy that over because let me just paste there. Yep. All right. So it's worth thinking about the colors that I've used here. Okay. So you can see that for each solution, the x value is growing by 4 there, and the y value is from one solution to the next on that line is going backwards by 3. Okay, so 1 to minus 2, minus 5, minus 3. And these pairs work, right? And so what if I was to put these in the table and I just make this dummy variable t on the left here, and so I've got 0, 1, 2, 3, 4, minus 1 plus, because I'm just starting off with this initial value x0, okay? And so, thank you. So this minus 1 is our initial value, and we add 4 to it by 1 in this when t is equal to 1, gets us to the next value. And we add minus 1 plus 4 times 2, well, that gets us to 7. Minus 1 plus 4 times 3, that gets us to 11. That should be an 11 there. And the 1 minus 3 times 0, so on and so forth. You can see that it does exactly the same thing. So weirdly, in some ways, the x values is growing by the value that in this case would be b, right? The value we're multiplying the y by, and our y is growing by the other number, the number we're multiplying our x by. So our family of solutions, if we were to follow on from this t, you could see that also, can I just go back and say here that, so our minus 5 and 4 is, I should write that over here, so minus 1 plus 4 times minus 1 equals minus 5, and 1 minus 3 times minus 1 equals 4. Okay, and so if x is minus 4, if x is minus 5, y is 4 there. So you can see here that for this case here, that would mean that t is equal to minus 1. So this is why we have like a family of solutions, okay? And if you're going to write it down in set notation, which hopefully we do start to do, so it's a set of ordered pairs, x and y, such that x is equal to 1 minus 4 times t, and y is equal to 1 minus 3 times t. And I should say it's minus 1 in the x there. For t is an element of the integers. Okay, so you could write them up here as well. X is equal to minus 1 plus 4t, and y is equal to 1 minus 3t for t element of integers. So the theorem actually states that, so x naught, y naught for our initial solution, if we can find another solution, there will be, so taking out this d as a highest common factor, this proof will step it out, so you can read it at this point. You can watch the video of me doing it as well, but this proof does step out and show that if we use the rules that we've learnt in exercise 2e about common factors and natural numbers, that the simple rule has to be true. Okay, so what have we got here? That x is going to equal this. Okay, so x1 is going to equal x naught plus b on d times t, and y1 is equal to x y naught minus b on d times t. So watch the proof. We'll talk about this in class. As part of the proof, I've got an extra adjunct to that as well, and that's definitely worth watching as well. Okay, and you can also potentially just read through the textbook if you're capable of that. So this is the example, and this is exactly the sort of thing that you would want to use a Diophantine equation, because we've got a thing here, notes that we can't divide. Okay, you get a $50 note or you don't have one. Well, you can have multiples of them, but you can't have half of them. All right, and so how many different ways can I have the $20 and $50 notes to make up my $200? So it's talking about his wallet, but this is actually something some of you have probably done in your head in the past. If you've got to take money out of the ATM machines, that's the machine, anyhow, ATMs, because they only give out $50 and $20 notes. So because we're talking about a real thing, we obviously can't have negative notes, and so there's a limit to the solutions here. But once again, there'll be a video for that, so you can go ahead and watch the video. Finally, I'm going to say that there is another solution which will make more sense after our next exercise, so you could probably get on and we'll understand it better at that point. But at this stage, you just want to remember it and work with it. Okay, but because a, b, and c and x and y must all be integers, then this ax plus by equals c has integer solutions if and only if that the highest common factor of the a and b, the two coefficients there, divides the solution integer c. Okay, so the example here, which I've just taken from the book, you can imagine 2x plus 6y equals 3. So if I was to divide everything by 2, that would mean that x plus 3y equals, whoa, we don't have an integer. Okay, so for that exact reason, the highest common factor has to divide c. And if you think about it, I'm not going to go too much into it, but you're more than welcome to tell me why you think it's true. There has to be a solution if that's true. All right, and here's the section summary. There's no point me reading that out. That exists there for those of you who are reading it. We've gone through it all already. Okay, just remember that so A, B, the coefficients are all integers. And of course the solutions x and y have to be integers as well. And here we have the formulas. Okay, and just remember that x naught and y naught, all they mean is the initial solution. So they could be any of them. Okay, as soon as you find a solution, that's x naught and y naught. All right, good luck. I'll see you guys in class.